Question 3, this part is coming from group 17. The halogens chlorine, bromine, and iodine show trends in chemical and physical properties down the group. The table here shows some properties of chlorine, bromine, and iodine. Color and state at room temperature. Chlorine is a green gas. Bromine, and they are telling us to complete. Bromine is actually brown and a liquid at room temperature. So I'll just say brown liquid. And then iodine is a solid. So you can say black solid. It is black or gray. Black or gray. But you write one of them. Then the bond energies, we can see that they are decreasing. Electronegativity decreases down the group. And then formula of the halide is that. Then Roman 2, the bond energy values in table 3.1 refer to X bond, where X is a halogen. Explain the trend in the bond strength of X to X bonds in halogens. So the bond strength, I think, keeps on decreasing because the bond energy here is decreasing. The stronger the bond, the higher the energy you need to break it. Okay. Now, we can see that as you go down the group, atoms become larger. Okay. Atoms become larger down the group. Then the distance. The distance between the electron pair, and the nucleus, and the nuclei of the two atoms, the two bonded atoms, is greater. It becomes greater as you go down the group. So you have this one here, and let's say this one here. This is iodine, so there is this one. Then there are electrons in here. So as the distance grows in between these two, the attraction here becomes weaker. And the weaker the attraction, then the smaller is that bond energy. You are going to break this one as fast as possible. So that is that. Then explain with the use of an equation how chlorine is used in the purification of water. State the role of the active species produced here. So we get water, chlorine plus water. We get two compounds. One is HCl, and then the other one is this other acid here. It can be written like that. Sometimes people write it like this. Okay, hypochlorous acid. And then the state the role of the active species. So the active species is actually this one here. Okay, from here you can get ClO minus. So this one here is the one that is responsible for the killing of bacteria. So we shall say HOCl or ClO minus is responsible. What is the role? I can actually just say this one kills bacteria. in that water, as simple as that. Then part C, the sodium halides in table 3.1 also show trends in chemical properties. Okay, identify the sodium halide that reacts with sulfuric acid, concentrated sulfuric acid, to form hydrogen sulfide. Of course, that one has to be sodium iodide. Sodium iodide. This is what happens. Let me write something here. You get sodium iodide reacts with conc sulfuric acid. So the first reaction is acid base. So this one loses one hydrogen from here. And then we get sodium hydrogen sulfate, then plus hydrogen iodide. Okay, now hydrogen iodide, as you go down the group, we have seen that electronegativity decreases. So the reactivity of these elements decreases. Why? Because the distance between the nucleus and the incoming electron, or the outermost electrons, it is going to be so big. And remember, these group 7 elements react by gaining an electron. So if the distance between the nucleus and the electron is becoming so big, the attraction is going to be weaker. Okay, so instead of them attracting an electron and gaining of electrons, implies that one which gains electrons is the oxidizing agent. Okay, because it is getting reduced as it does so. Now, for them to become, to become more of oxidizing agents, it has to be from up the group. So down the group, they become weaker oxidizing agents, but become stronger reducing agents. Now this one here is going to be reduced. It is going to be oxidized by sulfuric acid. So sulfuric acid is a strong oxidizing agent here. So we shall have hydrogen iodide, then plus sulfuric acid. Then we get iodine. By the way, there are 3 that you can get for iodine. There is iodine, then plus we have this hydrogen sulfide, and then water. Okay, and water. Another one can be iodine, you again put water. Iodine, you again put water. So there is sulfur, there is also sulfur dioxide. Okay, these are the possible 3 for hydrogen iodide when it is reacting. Now, I'm going to take off all of this. But for bromine, we just get, if we have hydrogen bromide to react with sulfuric acid, you're going to get bromine, and then sulfur dioxide and water. So the one that produces hydrogen sulfide is to do with iodine. Identify the sodium halide that only undergoes Bronsted-Lowry acid reaction with concentrated sulfuric acid. That one has to be sodium chloride. Okay, because here the HCl that you are going to form, remember, they all have the same reaction here. So here just put chlorine, then put chlorine here. So this HCl here is not going to be reduced by sulfuric acid because chlorine is a stronger oxidizing agent, and here sulfuric acid is acting as an oxidizing agent. So because chlorine is a stronger oxidizing agent than sulfuric acid, then it is not going to be oxidized. You see that? So that means this one is not going to be broken any further. But for iodine, the one of iodine and bromine, they are broken down. Okay, so that is why here we have sodium chloride. sodium chloride. And by the way, they said identify. So you can write the name or you can write the formula. Okay. Roman 3, a student adds a few drops of silver nitrate to a solution of sodium bromine. State what is observed. Of course, this one has to be a cream precipitate. Sometimes we say off-white. Cream precipitate. Okay, we have, from this one, we have silver ions. Then from this one, we shall have the bromide ions. Then when they come together, they form that silver bromide, which is a solid, and that is the cream precipitate. Okay, in the exam, you don't need to write this equation. You just need to write the observation. Me, I'm doing everything just to show you where things are coming from. Part D. Iodine monobromide is a dark red solid that melts near room temperature. Then iodine monobromide reacts with propene. The mechanism for this reaction is the same as the mechanism for that of hydrogen bromide with propene. That is what we call electrophilic addition. Okay. Then they are saying, Roman 1, identify all the intermolecular forces that exist between molecules of iodine monobromide. Now, the fact that bromine is more electronegative, okay, compared to iodine. Remember electronegativity. We are looking at that power to pull electrons towards the atom. So bromine is stronger in that, so it pulls the electrons towards itself. So iodine here appears to have lost electrons, so it's partially positive, and then this one is partially negative. So that means this molecule here is polar. So because it is polar, then we are going to have permanent dipoles. We actually say permanent dipole. Permanent dipole. Sometimes we say PD. Even this one is accepted if you do so. And then the other one, because this one is molecular, it's a molecule. So we have instantaneous. Dipole. Induced. Dipole. That is what we call IDID forces. These are the ones in between the molecules. Okay, so that is that. Roman 2, name the mechanism. I already said it. It is electrophilic addition. So this is actually what happens. You have propene, which is CH3, then CH, and then CH2. So you have iodine here, and then the bromine. So since this one is already partially positive and this one is partially negative, so as it draws near this molecule here, remember here we have electrons which are negatively charged. So this one here will be attacked, and then this one will go off. So meaning we are going to have CH3, CH, then CH2, and we can have iodine attached to this one, then this one becomes a carbocation. Why is it this one? Because this is an alkyl group. I'm also taking this one as an alkyl group here, then positive inductive effect here. Okay, so this is a secondary carbocation. That one is more stable than a primary carbocation. Then the bromine, which is broken off from here, will now donate its pair of electrons to this one here, and then we get CH3, CHBr, and then CH2. Actually, I always say here the rich get richer. So the carbon here with more hydrogen atoms, which is this one, okay, is going to receive the electrophile first. That's why we say electrophilic addition, because this one appears to have lost electrons. It's an electro. Electro means comes from electrons. Then phile is love. If you love electrons, that means, remember, electrons are negatively charged. That means you are positively charged. You see that? So that is the simplest way I can explain that, or you can term that. So the rich get richer. So the one rich in hydrogens gets first. But there is also that scenario where this one who is poorer, the one which is poorer, can now get the electrophile first, and then you can get iodine here. Now you will have something like this: CH3, CH, then iodine, okay, then CH2. Now this one will be the plus. Now this is one alkyl group here, okay. So then when bromine comes, it will be here. So you see that one gives us a product which is coming from a primary carbocation. You see that? So those are the two structural isomers which we can get from there. So in fact, I can write this one here and I put Br, and then I can write CH3, CH, this one, the major one. This is major, this is minor. Let me even put this one as major. So CH3, CH, then Br, and then CH2, then I. So why is this one major? It is major because this molecule here is going to react with this one, with this side. This side, which is positively charged, is the one that is going to attack this part here, which has the electrons. So it will attack with the positive side, which is the one of iodine, okay? So they are saying identify the type of structural isomerism shown in these molecules. Of course, this is position, okay? Positional isomerism. We can see that the bromine is here on the second one, but then here it is on the first one here. So like that. Then Roman 5, explain why the two structural isomers do not form in equal amounts. That's why I say this one is major, this one is here is minor. So why don't they? So we have the electrophile. Electrophile approaches with iodine first, okay, with iodine being the nearest, okay, not with bromine, iodine nearest. Why? Because this one is negatively charged, the electrons, and this is positively charged. You see that? So there is that attraction. And then we can have iodine. First of all, this one is polar. This molecule here is already polar. So what brings about the polarity? You also talk about it. You say that iodine and bromine are have have different electronegativities negativities or the same way I can say this one is iodine bromine is a polar molecule. It's a polar molecule. So the attack has to be from the positive end of this molecule for iodine. So if the attack is from the iodine side, the product is going to be formed from the secondary carbocation. You can even say major product is formed from the secondary carbocation, which is more stable than the primary carbocation, like that.